having h akh j omega 0 equal to minus 1, what does it mean? It means that the module of j k omega 0 is equal to 1, and of the phase is equal to 180. Okay? So, this is condition for instability. Also covered condition. Okay? So actually, if we want a system oscillate, this should be the case. But we don't want our system oscillate. We want number 5. Okay? So we would like the opposite of it. We would like this condition never happens. Okay? Clear or not? So actually, now what we write that this condition should be never verified for a linear amplifier. This should never happen. So, let's consider we have this here. We have this here. And actually, if we have the condition on instability is the shifting of 180, okay? Shifting of 180, what does it mean? Shifting of 180. So, shifting of 180 is like that. This is here, okay? Shifting of 180, it's like that. Okay? Shifting of 180. So, but actually we would never want this condition, okay? Because if this is exactly 180, actually is a opposite. It's not a negative feedback anymore. This is kind of became a plus, okay? But actually, in order to not let the system diverge, this actually not only should be equal to 1, but should be usually never being larger than 1, or 1 or equal to 1. So actually, the condition for non-instability is k j omega 0 module lower than 1 and k j 0 different than 180 better to say, with some margin, and we will see later what I mean. Okay? Okay, it should be larger than 180. Yeah. And so actually this is supposed to be so I mean with some margin means usually larger. Okay, but we'll see that what does it mean. Better larger than 180. But we will see, okay, because as it's periodic, as plus 180 and minus 180, I mean, is the same actually, okay? Then we will see better what they mean here, okay? So actually, we would like to be in this condition. So the gain always lower than 1 for each frequency. The module. So at the frequency. Yeah. So the frequency should not be the frequency for which the gain is equal to 1 and never been equal to the phase, the frequency for which the gain is unitary. The phase should be far from 180 degrees. Okay? So this is condition for non-oscillation, but we will see, I mean, to really understand this, we need to do some draw, okay? Because I understand that at this moment is not clear. So now we need to go back through some bases and remind both the rules, okay? So this is actually as a theory. You have, this is a kind of mathematical basis. We have this transfer function. With this, we don't want that it never goes to infinite, okay? We don't want that it diverge. So this is the condition for which it diverge, okay? But what we just consider, just looking at this, that if we really don't want to diverge, okay? If you don't want to be amplifying to the diversion, actually need some kind of attenuation. So actually this, instead of being, it cannot be larger than 1, okay? Actually, this is the so-called oscillation of Barkhausen, but it still oscillates even if it is larger than 1, okay? So this is condition of Barkhausen for which I oscillate, but also oscillate if the gain is larger than 1, okay? For the phase equal to 180. So the condition for the stability will say that is this, but is also this. If the gain is equal to is larger than 1 and the phase is equal to 180 degrees, this is oscillate. In the opposite condition, it will not oscillate. So, okay, now I cancel out and I just go step by step to understand this concept. Okay? So I mean I can understand that as of now there is kind of a fog in your mind. I hope that at the end of this, I mean in 1 hour everything will be more clear. Okay, let's clarify all the concepts. So actually, both the rules, what does it mean? both the rules. Actually, what we have, both the rules say that whenever we have a pole, actually, what do we have? This is transfer function module, and this is phase, okay? So actually, whenever we have a pole, if this is a pole, okay, what happens to the phase? What happens to the phase is that at the frequency of the phase, actually, we have a phase of minus 45 degrees, okay? And this phase shifting became minus 90 degrees at decades later. So if we have omega p here, we have 10 omega p. Here I have minus 90, and a decade before I have 0, okay? So if I unify this point, this kind I have something like that. Okay? This is what happens with a pole. Okay? Behavior of a pole. Let's look about the behavior of a zero. Okay? If I have a zero, actually at zero, what happens? Okay, this is a variation of minus 20 dB over decade. At zero, let's consider here omega z, we have a variation of plus 20 dB over decades, okay? So this is the module. This is the phase. So what happens? Specularly, what happens to the pole? I have 45 degrees at the frequency of 0. I have a 90 degree plus 90 degree at the frequency at a decade later. So 10 omega z, and actually 0 shifting at dot a decade before. Okay? So actually what I have here, I have minus, I have 90, okay? And here I have 0. So, the curve is like that. Okay? Okay? So notice that this is asymptotic towards 90, and as well as asymptotic towards minus 20, okay? It reaches so-called at the infinite. Okay? Similar here. Okay, this is a kind of, if it is minus 90, reach to the infinite, so it's asymptotic. Okay? Good. So, let's move this from this theory to the circuit. Okay? Let's do at first small step. I consider, for instance, what happens if I consider two common sources in cascade. Okay? One. So this is one. Then I consider here another source, common source, R2. Okay? VDD. This is in. actually, what are my poles? My poles are, okay, immediately at the first sight, by inspection. What are my poles? Omega 1 equal to? Huh? Omega 1 is equal to 1 omega R1 C1. Okay? Omega 2? At the first sight, by inspection, okay? I see here two capacitors, two main capacitors. I consider the capacitor, I consider the resistance at the same node. Here I have not capacitance across node, okay? I have just capacitance between a node and ground. So I just look at the capacitance. Each of it give me a pole. Then I consider the resistance that are insisting on that capacitance on the C1 in system 1. So I have the pole, respective pole 1 over R1 and C1. And omega 2 is equal to 1 over R2 C2. Okay? So what does it mean? Okay? It means that if I want to draw the plot, what I have, I consider here one pole and here another pole, okay? So DC gain, what would you be the DC gain? If it is M1, it is the M2. DC gain, what does it mean DC gain? DC gain is GM1 R01 R1, okay? This is the gain of this stage multiplied by the gain of the second stage. R2, R02, parallel R0, R2. Okay? This is the DC gain, the gain of each stage. Okay, the DC gain that everybody we know. Okay? The multiplication of the gain of the single stage give the overall gain. This is the DC gain of the first stage. This is the gain of the second stage. Overall is the gain of the entire stage from the beginning to the output, from the input to the output. Okay? Then we have a pole. Then you have another pole. Assuming that C1 is a larger, okay? Assuming G1 larger than G2, we have that the dominant pole is the first one, okay? Dominant pole is the first one, and actually the omega 2 is the secondary pole, okay? Omega S, secondary. Is dominant is second, okay? So actually what you have, dominant 1 over R1 C1, and here 1 over R2 C2, okay? Why drawing this? To just show you about the behavior with respect to the phase, okay? So okay, so here I want, this is the module of V out over V in. This is the phase of V out over V in. Okay. What do we have? Okay, here I have first pole. Here I have second pole. Okay. Let's consider this is the after. Okay. This is then omega 1, omega d. This is 1 decade earlier, so 0, 1, omega d. This is a decade earlier, so let's call it, okay, 0, 1, omega s. Okay, this is omega s, and a decade later will be let's consider, just change the slope. Let's consider here, okay? 10 omega s. Okay? So I connect the point. Okay, I need to draw it here. Here, what? Here I have, let's say, minus 45. Okay? Here, minus 90. Here, minus 135. Here, 185. No, 180. Okay. Okay. Here, at the first dominant pole, I have a minus 35. Okay, minus 45. At the earlier, I'm 0. At the after, I have a minus 90. Okay. So here I can draw this as a phase. Okay. Then what I have? At the second pole, something similar happens. Okay. Second pole, I have a further shifting of 45. Needs to be divided. A minus 45, this pole has effect, and actually his slope starts to decrease when I take the earlier, so here. And the still final shifting of further 45 degrees, so till 180 happens at the later. Okay? So actually what I have, the overall phase is like that. Clear or not? Clear? So, what? So I ask you a question, okay? Question. Can I cancel this part? I cancel this part, okay? So this is why now you understand why the phase matter. Okay? For the instability. Okay? Actually, because going towards 180, the signal is kind of swapping, having a minus on it. So it's supposed to. So having a signal shifted by 180, this means having the kind of the swap of the signal towards this DC point. I don't know if is what I draw you before, right? If you have a kind of a signal like that, so having of a swapping, this is swapping, okay? So having a signal shifted by 180 is the same actually, okay? If this is cosine di omega t, okay? This is cosine di minus cosine di omega t, il minus, and this is cosine di omega t plus half phi, where this phi is 180, actually is the same of having a swap in the signal. Okay? So far so good? It's clear or not? Actually it's what I showed you before. If I just keeping delay, it's like having the positive feedback instead of the negative feedback. Okay, sorry, I also delete this. Okay, so this is, of course, open loop, okay? Open loop. But open loop, what does it mean, open loop? It means that actually is my HS. Okay? Is the one, if you remember, this is open loop system, but if I would like to put this in a feedback, I would like, at the end I would have this, okay? 1 plus KHS. Okay? And actually, which is the so-called, the scaling condition? The scaling condition for this, that means instability, is the condition for which I have this, okay? Okay? This is condition of instability. Okay, as we saw before. Okay, actually, now we have this is the transfer function of open loop transfer function HS. Okay, of the system, and this has this characteristic. Okay. Actually, as I told you, usually H, for simplicity, just a resistance. So actually, has a component that does not change over frequency, are not active element. Okay. So actually, I may write that this condition is also what? Is also simply this condition. Okay. Because usually this is not, it's just a constant, okay? Has no any phase. So this is a risk to go in the instability or not. Let's see. So this condition can be ever verified or not. Okay, when the gain is equal to 1. So I need to be far from this condition of instability. When the gain is equal to 1. Gain is equal to 1 here. Okay? This is the condition you need to be far away. Gain, when it's on the, as this is the dB scale, okay? dB scale, dB log scale. This is the value for which I have instability. I mean, the value for which I risk to be in the stability in the case the phase is equal to 180. Okay? Okay, now you can tell me, okay, but here, I mean 180 minus 180. Actually, which is the phase of this omega t? Is is roughly minus 180. But actually, this is kind of a phase, okay? And do you agree with me that phase of 180 and phase of minus 180 are the same? Do you agree with this concept with me? No, I guess not from your face, but okay, actually. Okay, the period overall is 360, okay? So, if the period is 360, if I shift, if I delay, or if I anticipate by 180, it's still the same, correct or not? I think maybe, okay. Okay. Now I give a shifting of plus 180. Shifting, phase shifting, okay? Phase shifting of plus 180. Plus 180 means that this point was here, and so on and so forth. So actually what I have fish shifting of 180 is kind of having this. Okay? Shifting of 180. So if I, on the contrary, if I shift of minus 180, what I have? I have actually something like that. Okay? This point now is here. So, you see that in both of the case, I have two signals opposite to each other. Okay? So shifting by 180 or shifting by minus 180 is the same. Agree with me? Good. So actually, this is the odd frequency, the odd phase to take in account. There is any, so I ask, is there any omega 0 so that h of the frequency, the module of that frequency is equal to 1 and its phase is equal to 180? Question. Is there any frequency for which my open loop system circuit has the gain unitary and the phase equal to 180? Actually, when the gain is unitary, at the crossing point. Okay? Crossing point, as I told you here, is kind of asymptotic, okay? So actually, being asymptotic, I mean mathematically not, in practice really far, okay? In practice, I'm really scared that if I just place a feedback loop, this network could go into instability. Okay? So, because here is very close to this value, okay? So actually, what I need to do, if you just look at this network, okay? I want to be as far as possible to the value for which my transition frequency is equal to, as a phase, as the correspondence phase equal to 180. So actually, what we can act? Actually, what I want to do is that this, instead of being here, is far away from this line. Okay? For instance, I would like this value to be here, so that I'm far from this value. Okay? And all this can be done. Actually, I can do, for instance, by what? If I increase this capacitance, okay? Plus C, I mean overall plus C1 first equal C C compensation, okay? Let's call it C compensation. And they move from this value to, let's say here, okay? So now I have this new pole 1 over R1 C compensation, okay? Let's consider it here. So what does it mean? It means that this is backshifted, okay? And then continue the same. But what happened to the gain? The gain, because of this higher capacitance, now it's like that. Okay, the pole is here, so actually the inclination now is here. Okay? So here, the second pole is here. Okay? So now, the new omega t is here. Okay? Omega t first. What does it mean? It means that the value for which the frequency, the gain is unitary, has a phase that is far from 180. Okay? Okay? So, being the frequency for which I have a phase far from 180 makes our system more stable. Okay? This is the kind of line of instability. Okay? If omega t, if the crossover gain value is omega t has a phase that is closer to 180, I'm closer to an instability. Okay? Because I'm in the condition of instability. Okay? If I'm able to just have this frequency the crossing frequency of the curve of the gain that is far from 180, actually I have a stability. Actually, increasing this capacitance, okay, reduce the bandwidth, but let us being far away from the instability. Okay? From your face, I see that most of you is not clear. So, I repeat once again. We don't want that there is no any frequency for which the gain is 1 and the phase is 180, okay? 180 and minus 180 is the same, we say, okay? So, should not never happen because this is the condition for which this diverge, okay? This diverge. So I always want to be far from this condition. This is, as you see here, omega t is, just in the first plot, the line in blue, this frequency, that is actually the frequency for which this gain is equal to 1, implies a transparent function having a phase roughly equal to 180. What does it mean? It means that if we place this open loop network into a feedback, most probably, almost for sure, the system will be into instability. Okay? So, by reducing the first pole, by increasing the capacitance, what I did, actually you can check mathematically, just visually. I just reduce the value of the transition frequency, okay, this omega t, so that the respective phase of my transfer function result to be far from 180, okay? And of much far. Actually, of much far is what is called phase margin, okay? So how far is from the instability? How far it means is the phase margin, okay? So far so good? So actually we can call it. Is clear or not? So actually here, this is omega t. These need to be omega t, need to be always lower than the frequency for which the phase is 180. Okay? In this case, is roughly equal to omega, the frequency for which the phase is 180. Okay? I call it this omega p, omega pi. Okay? So, previously it was roughly, was unstable, okay? Because it was much closer to 180. Based on the addition of another capacitance, I move this transition frequency to a lower frequency so that the respective phase goes far away 180 degree. Okay? So, in this way, I move to the stability because once I place this network into a feedback loop, actually, most probably it will be, will be stable, the overall network. Okay? Actually, I look. What is remarkable? It's remarkable that I look. This needs to be also clear. Okay? So, I look at the open loop transfer function to check stability in the closed loop system. Okay? So now let's do another example. Okay? Can I cancel? Actually, these concepts are, really easy to fly us away. Okay? These concepts need to be fixed and repeated in your mind several times because they are easily to be flying away. Actually, we study open loop transfer function to just dealing with the stability in the closed loop. Okay? Okay, so just to summarize once again, stability, condition. Okay, let's consider 3 possible scenarios, okay? This I have H, this is module, okay, in the B, and this is the face. So let's consider 3. Three possible condition. Minus 100, okay? Okay? This is the face. So let's consider 3 cases. 3 cases that I have. Here my omega 0, and here my omega 0. I have here here my omega C, omega T, and the omega phi. Okay? Here omega 0, omega, we call it omega 3. Yeah, the same. So omega t, they crossing the same point, okay? Here I have what? This is omega t, this is omega phi. This is omega t, and this is omega phi. Okay? So I call it omega t is equal omega 0, so that the gain is equal to 1. Okay? Omega pi is the frequency so that the phase of H omega 0 are equal to 180. Okay? Okay, so we want to have this far from this. So we say that this is kind of unstable condition. Okay? This is again unstable. This is stable. Okay? So far so good? Okay, so maybe we can also call it omega t, like gain crossover frequency. These two need to be always lower than the phase crossover frequency. Okay? This is condition of stability in closed loop of condition of stability in closed loop of a open loop system. Open loop system. Okay, so actually what is remarkable is that we look at the open loop and the feed-forward network to just find out how would be the stability of the feedback system. Okay? So these are the conditions of stability. Okay? We do an example. Can I cancel out? Is clear or not? Can I cancel or not? Now we do again another example, okay? Can I cancel? Okay. So I have this network, okay? Let's do again a simple network. R1, C1, R2, C2, R3, LCD, okay? Here the in, and this is the out. Okay? So this is kind of open loop, okay? But I imagine the question is that if I just consider here this network, okay, into of a feedback, okay? So if I place my open loop circuit, okay, open loop means from here to here. I specify forward, forward path. Okay? Into a feedback system. Shall the overall system be stable? Okay? Why I want to underline this actually? Because for studying the stability of a closed loop system, we just refer to the open loop, to the feed-forward path only. Okay? Okay? So actually referring to this transfer function, we study the stability of the overall system. Okay? As we know already, the Barkhausen theorem, the Barkhausen condition that need to be avoided. Okay? So, I just draw again. Okay, I need to take care about the quality of the draw, otherwise you don't understand that. Okay, I hope to take 45 minutes and we go for lunch at 11:50. Okay? To exploit my lack of expertise in drawing figure that I need to do. Okay, so of many polar here. Of many polar here, please. Look at the system, open loop system. Of many polar here. Hello? Three. Why? Why three? Why three? Why three? Because I have three capacitors, okay? And so which are these three poles? Which are these three poles? These three poles are? Which are these three poles? One R1 C1, then one R2 C2, and the other one R3 C3. Okay? Easy. Okay? So the first side we see the pole. Okay? Okay? This is actually what we need to avoid, okay? I'm just drawing it in red. Okay? This is the wall of the stability. Actually, you consider this. First of all, let's say here. Okay. Omega. I call it omega d, okay? Without specifying which is the smallest. Omega d. Then I place another pole, let's say here omega s. Okay, you see much more slope from here. Okay, and then okay, here omega s2. Okay, two secondary points. Okay. Okay, so let's draw the phase. So what we know that in correspondence of a pole, I have a shifting of 45 that became 90 and 1 decade later, and starting from a decade earlier. Okay? So what I have? I have that. Here I have a minus 40. Okay? That a decade later, it's 90. And a decade earlier is 0. Okay? Then I know that the next affect what? Additionally 45. Okay? So here I have what? 90 plus 45, 130. And it starts a decade earlier. Okay? And actually became my additional 45 1 decade later. So actually 1 decade later I have 180. Then I have a third pole, that actually additionally 45 at its frequency, and additional 45 1 decade later. Okay? It's clear I get this point. So this I am 45, that became 90 a decade later. The second will be additionally 45, that became additionally 90 1 decade later. Okay? So actually the phase is like that. Okay? Clear? Okay, where is omega omega t now? Omega t is here. Correct? And which is omega pi? Omega pi, let's say, crossing here. This is omega pi. Okay? So we have omega pi that is lower than omega t. So unstability. Okay? Okay? So far so good? Clear or not? Clear? So actually we have that our crossing gain crossover frequency, omega t, gain crossover frequency, has a phase that overcomes the barrier of 180, okay? And this means that if I place this network into a loop, my feedback system would be unstable, okay? And we need to fix it. Okay, of course, if you want to do a feedback loop, if you want to let it operate in open loop, I mean, no problem, okay? Open loop, that's it. Whatever is affected, the gain of one stage is will affect the stage of everything. If you want a feedback system, if you use this network, once you have into a loop, it will be unstable. So, what we can do to make this more stable? Huh? Question, what we can do to make it more stable? How? Okay, move this IT of VT. I mean, should be more here, right? How? We saw this already, right? We saw this already, right? So what we can do? To do that, actually, what we can do is add the capacitance here, okay? Okay, just look which is the dominant pole. Dominant pole, let's say that is this, okay? Let's imagine that this is omega d. So omega d, I had here additional capacitance, okay? C1 plus, okay? So that's what I do. I move, actually, this node, this pole, at a lower frequency, okay? So I want this to move it here. So actually what I can do, I look something like this is shifted here. So actually what I do is actually moving this node, this pole, a much lower frequency. So what happens? If I move a much lower frequency, higher ever. If I have the pole here, what I would have? I would have something like that. Try to do the drone at my best. Move the pole here. Okay, the dominant pole is moved here. So actually I have a different gain profile. Okay, so this actually is parallel with this. Okay, these are in parallel. Okay? Then these are again in parallel. Okay, actually, it's not enough. So I need to shift the more. Okay? So this is in parallel with this. And this is in parallel with this. Okay? So now I delete. Okay? So what I did? I move back this pole, the dominant pole, by mean adding a capacitor. Okay? So that now my crossing frequency is here. Okay? Being a crossing frequency here, it means that omega t now is lower than omega pi. Okay? So we move towards the stability. Okay? So, actually, now the distance between this and the 180, this is called phase margin. Okay? A good phase margin is usually around 60, 70 degrees. Okay? So actually this is a kind of a number, qualitative number, okay? We need to be far from this wall, okay? How much far? If you have far of 60, so actually far of 60 or 70 is better. So you need to be far from this wall of 180, because then they find out instability. Okay? Just the last remark and then I'll let you go. So this is called dominant pole compensation. Okay? Dominant pole compensation. Okay? But what do we know? That we can do also another kind of compensation. Actually, we add the capacitance here, okay? We add the capacitance here. But what happens if we add the capacitance here? If we add on purpose, okay? A capacitance here, Cm, similar. What happens is that equivalently we can also consider a capacitance here. Okay? But exploiting the Miller effect. So actually it's better having the capacitance here than having the capacitance here. Because in this way you can exploit the gain factor. So actually you can reduce the value of the capacitance you add. So for instance here, you add the capacitance to move with the dominant pole, you add for instance the capacitance C1, okay? C1 first, with the dominant pole compensation. With the Miller effect, you can get the same effect with a capacitance that is smaller by the gain of the stage. GM R D2. Okay? Why? Because this is affected by Miller effect. So when you place these equivalently at the beginning, at the input on the stage, actually with a smaller value, with a smaller value of the gain, actually it has the same effect. So having the capacitance here, having a capacitance C1, or having a capacitance that is the gain times smaller here is the same because of the Miller effect. Okay? So this is pole dominant compensation. When I add the capacitance here, which have the same effect with a smaller capacitance. Okay? So still move the pole here. So Miller effect compensation allows adding lower capacitance value. Having the same effect. Okay? So, and actually time is over. Actually, when we deal with an OTA, actually that's exactly what we do. Okay? What we do is operating this Miller effect compensation. Having the pole shifting to get the stability. Okay? Is exactly what we get with the. So actually, if we have something like that, usually, okay, here we have 5T OTA. Okay, here you have the second stage. Here you have a kind of gain. Here this is a mirror. Okay. Actually, what we do is adding here how. Oh, this is good. Okay. The Miller capacitance is here. Okay, this is a common source stage. So actually, what we do is placing this to adjust the pole. Okay, to adjust the pole to having a Miller effect compensation. Adjust the pole to let my system being more stable. Okay. So and with this, that's all with stability. If you have any question, please let me know. Now maybe I leave the stage to Professor Buy that talk about what else is needed to set your card, and then we come back on this as well. So I leave it here, please. Thank you.
Thì có một vài vấn đề chúng ta vừa phát hiện ra là cái con wifi kia nó đang chặn cái vị trí IP ấy, do vậy là đối với những người nào mà có cao của viết thì không ảnh hưởng gì cả, còn những ai mà hiện đang dùng cái máy ảo ấy thì mọi người connect vào cái mạng IPI meeting 503 thì cái con đấy từ nửa ổn định không chặn cái địa chỉ IP kia. Đấy, chỉ có một cái đấy nữa. Thì các anh chị nếu mà các anh chị có thể lên đây và ngồi đây để làm cái